Включите също ми видео. Отлично. Good morning, dear colleagues. Good morning from Athens. On behalf of organizing committee and all committees of our conference, I'm very glad to welcome you in Greece, in Athens, and in the 13th International Conference of DESSERT' 2023. We're very glad that is the second time that this is held in Athens, in Greece, and also we're very pleased that we have successfully the 12th International Conference in Greece, and after that the organization committee decides to continue in Athens in Greece and support our colleagues' residents in Ukraine in this terrible time that with the war. The scope of our conference, of course, is known to all of you, and Professor Hartcheko will continue on that. It's, of course, to support our colleges and the science and keep on going on this term and this year. Our conference will have our proceedings again in IEEE, in X+, and more than 100 papers that year we have accessed and will present it in these conferences. We have, of course, all committees. Thank you for your contribution and your support, and special our sponsors of organizations that again and more this time support our conference. With finishing my speech, the short speech, I'd like to call some of our colleagues from sponsors that are supposed to give some regards, some words, and start. And I'm glad to start with our Dean of Hellenic Army Academy, Professor Kaimakamis, to have some words for our conference. Please, Yorgos, you are welcome.
Thank you very much, Nikos. Good morning to everybody. Dear ladies and gentlemen, as a Dean of the Hellenic Army Academy, I'm pleased to welcome you to this very nice, very productive, I think, conference. I think that this conference is for the second time in Athens, and I think that through the conference that you are going to exchange ideas and knowledge, that it will be very good for a better and safe world. I think that I want to congratulate the organizing committee, and I wish you to all a very productive 2 days conference. Thank you very much, Nikos.
Thank you, Professor Kaimakamis. He's very glad that in our university is the second time that is held this very important conference, and we hope to continue in that tempo. Thank you very much. Also with us today is the main support is IEEE section support and presentation of University of Thessalia and special department on informatics for bioinformatics. Please, Professor Kakaroudas.
Thank you very much, Nikos. Dear organizers, dear researchers, dear participants, it is such a great pleasure for me to represent the Department of the Computer Science and Biomedical Informatics from the University of Thessaly that organizes the 13th International IEEE Conference on Dependable System Services and Technologies. And I'm here also representing the IEEE Greece section that technically co-sponsors the conference, showing once more its focus on science and research that unites us all. The conference is organized by respected colleagues of the academy and industry, who I want to thank personally and congratulate for their hard work. They managed to bring to us a rich technical program of high quality. It is amazing. Under the dark clouds of war in Ukraine that traditionally hosted this conference. In fact, the Department of Computer Science and Biomedical Informatics constantly supports scientific and research events like this, conferences and symposia, and presents special interest for events organized with scientists from all around the world. The first time that we learned about DESSERT' 2022 will take place in Greece. We have become part of it, supporting the efforts of our colleagues from the Ukrainian section. And here we are again today in 2023, showing that our support is constant. It was not an opportunistic or something that temporarily happened. We are here showing our solidarity as scientist to scientist. I strongly believe that apart from the technical part of the conference, this is a great opportunity for Ukrainians and the rest Europeans to discuss on potential collaborations and hosting Ukrainian researchers to universities and research centers until this war comes to an end. As the head of the Department of Computer Science and Biomedical Informatics, I would like to greet the organizers of the conference, the respectful authors, and the participants, and wish for productive and insightful works of the conference. As the conference liaison of the IEEE Greece section, I also wish you the best in your works and have a productive today's conference. Thank you.
Thank you, Thanos. Thank you, Thanos. Thank you, Professor Karoudza, very much. And to congratulate you, of course, for your new position of the head of department, and continue our contribution on that. Thank you very much. After that, we call co-chair of our conference, Professor Hatchenko, for a short presentation of the history and the scopes of our conferences. Please, Professor.
And thank you very much, Professor Nikos Barnets. First of all, I would like to thank our Greek colleagues for possibility to organize this conference in Athens. It's a beautiful, very famous city in the world, and our conference will held in a mixed format. This conference is a 13th conference on dependable system services and technologies, and this conference is dedicated to dependable and trustworthy artificial intelligence, Internet of Everything, big data analytics for safe and secure work. It's very important for all world now, especially for our country, because we have terrible war with Russia for our freedom, for freedom on Europe. And I would like to say a few words about our history of our conference. We started 17 years ago in the beautiful city of Ukraine, in Poltava, in the base of Military Communication Institute. And then we started with our colleagues from military academy, and now it's small tradition on our conference communicate with universities and with military institutes as well. Our next conferences in 2007, 2011 were held at the at the base of research and production company RADI. It's one of the famous our manufacturer, which is leader in development, production and maintenance of instrumentation control system for nuclear power plants, for other critical application. And during 5 years, we held our conference in Kirovograd. Now it's city Kropivnitsky, on the central part of Ukraine, very famous historical place of Ukraine. Our next conference in 2012 was held at the base of Banking Academy, Ukrainian Banking Academy in Sevastopol. We held one conference and one workshop, DESSERT', in the Sevastopol. Now this city is occupied by Russia. Our next steps with moving of conference was in other cities of Ukraine, in Kiev, in Chernivtsi. We held in 2014 and 2016 and 18 three nice conference on the base Banking University in Kiev and in Chernivtsi National University, the western part of Ukraine. In 2019, our conference was invited by Leeds Beckett University in United Kingdom, and this university beginning this time became one of the co-organizers this conference. And 3 years ago, we held was our online conference caused by COVID-19 in Kiev and Kharkiv. It was online conference in these cities. You see center of our city Kharkiv is one of the biggest square in Europe. Sorry, but now about 25 buildings of Kharkiv were destroyed by Russia troops. And last year, as said my colleagues, we continued our conference in Athens, and thank you very much for this possibility. And now I would like to say about some statistical metrics of our conference. 114 papers have been accepted, prepared by 342 authors, and will be published in the DESSERT proceeding to be included in IEEE Explorer library and Scopus indexed. We have a very representative international community from 15 countries. It's our authors, our keynote speakers from Belgium, Czech Republic, France, Georgia, Germany, Greece, India, Italy, Morocco, Poland, Portugal, Slovakia, Ukraine, United Kingdom, and United States. Each paper has been reviewed by at least 2-3 reviewers, according with our procedure. We have very good program, 6 plenary sessions, 9 topical sessions, and 6 workshops. Especially thanks organizers of these workshops dedicated to critical data processing system modeling, intelligent cyber physical systems, human machine cooperation in critical systems, digital infrastructure for small module reactors and energy grids for safety and security, dependable aerospace systems, and intelligence for security and safety. Many thanks our keynote speakers. We have a very nice, very representative team of our keynote speakers. I would like to represent them. First one is Professor Patrick Anaf from École Nationale d'Ingénierie de Brest, France. Professor Alexander Letichevsky from the Glushkov Institute of Cybernetics, National Academy of Science of Ukraine, and now Alexander represents Heriot-Watt University, Edinburgh, UK as well. Professor Inna Skarga-Bandura from Oxford Brookes University, United Kingdom. Inna represents Ukrainian universities as well. Professor Gia Serbiladze from Javahishvili Tbilisi State University, Georgia, and Professor Alex Yakovlev from Newcastle University, United Kingdom. We invited very interesting talks from industrial domain. We have very good industrial speakers as well. It's Irina Leroy from European Security and Defense College, Brussels, Belgium, and Irina represents Worldline Sana company and University de Lorraine, Nancy, France. And our traditional industrial company, industrial guests from Infineon Technologies, Ukrainian Germany company, Dr. Alexander Karpin, Dr. Orest Akimishin, Dr. Viktor Kremin, and Alexander Pirogov. On Sunday, we will have very interesting special event, which will dedicate to space civilization development. This event will be organized by Professor Andrzej Rusiński from New Hampshire University, United States, and Dr. Tadeusz Kochanski's Sensor Signal System Lexington from United States, and film director and independent producer Dr. Adam Ustinowicz from Poland. Welcome to all these talks, all this event. We hope for interesting discussion of these topics. Short information about timetable of our conference. You received general and detailed program before. We have standard program for morning session. Our morning session will be in plenary modes. After that, will be held workshops, special sessions, and so on. Particularity of our conference is mixed mode. Yesterday and today and on Sunday we will have online mode, and tomorrow, in Saturday, after coffee, after lunch, we will have offline modes in the officer club in the center of Athens. The presentation timing is very simple. we have about 40 minutes for our invited keynote speakers and 5 minutes for question and discussion. And session talks about 20 minutes, and we will ask our moderator to check time and manage this session. And our second half day's timetable, if you have any question, welcome to for us. Organizers of our conference, one more, I would like to thank our host, is the Hellenic Military Academy, Athens, Greece, and the organizers of this conference are National Aerospace University, Kharkiv Aviation Institute from Ukraine, and it's my pleasure to say thanks from our university, from our rector and our city and country for that. Other organizers are University of Thessaly, Lamia, Greece, Polytechnical University of Morocco, Ionian University Corfu, Greece, Leeds Beckett University, United Kingdom, Institute of Information and System Technology, CNR, Italy, Lutsk National Technical University, Ukraine, and of course our colleagues from IEEE Greece section. Our special thanks all colleagues from organizers and international program committees who hardly worked to prepare this conference. Sorry for some problems with time because preparation of our conference was very difficult, caused by the war in Ukraine and other circumstances. Thank you very much, our partners and sponsors from company Infineon, Radi, Ukrainian Scientific and Educational IT Society. Thank you very much, all participants, for your cooperation, for your contribution with our conference. And our traditional photo with wishing of successful DESSERT conference on this three language, English, Greek, and Ukrainian. Thank you very much for your attention. And if you have a question, please, you can ask. Okay, we have a few minutes for some information from our head of administration team, Dr. Artem Perepelitsyn. Artem.
Thank you. It's a pleasure to take a part in DESSERT conference every time. And as it was told, there will be 3 parallel threads in each for each day, and for each authors it's necessary to check carefully the position at the program of the conference to find his reports and to find the required link to access the subsection, and to inform the moderator of this section that he available for report. And please follow the provided updated version of the program. You can find it at your email address, and please check it because sometimes the program may be updated. And as it was told, please try to use your time slot of 20 minutes to provide all the results of your research, of your presentation, and leave some time for the questions and share the results of your interesting science result of the research. Actually, this format will be continuously supported during all 3 days of the conference. So please check the newest versions of the program at your email, and please check where you are at this program with your report. And according to this information, please attend the required section. The plenary speakers and the section 1 will be at this meeting. The section 2 and 3 will be in parallel meetings. And after the lunch and periodically, all our guests of the conference should return back to this meeting to attend the plenary sessions. And again, thank you for attending of the DESSERT conference. Thank you.
Thank you, Artyom. And now we will continue our plenary session. It's our pleasure to invite for first keynote talk lecture our colleagues from France. Welcome, Professor Patrick. I would like to invite you for your talk, Adaptive Central Pattern Generators to Control Human-Robot Interaction. Before start of keynote, I would like to say about Patrick. Patrick is Professor Science in September 2013. Patrick obtained a master degree in robotics from University Pierre at Maine Curie in 1989, and a PhD in robotics in 1994 from Robotics Laboratory in Paris, University Pierre Marie Curie. From 1997 to 2013, he was a lecturer of Technical University of Serge Pontoise. He worked as a professor at École des Mines de Nancy of the University of Lorraine since September 2013, and in the L'Oréal laboratory, the part of CNRS UMR 7501 in the neurorhythmics team. He was a head of complex system, artificial intelligence and robotics department in L'Oréal from 2015 to 2022, and head of computer science department at Nancy from 2018 to 2023. Since October to 2023, he is professor at École Nationale d'Ingénierie de Brest and do his research at the lab STICC laboratory. Professor Patrick is a famous scientist in area bio-inspired control in robotics. And this topic is very important for our conference, for the world in the general, is a hot topics in the science, in the practice. Dear Professor Patrick, welcome to our conference, and many thanks for your contribution with the DESSERT conference. Thank you.
Okay, thank you, Professor Karchenko. Do you hear me clearly? Yeah.
Yes, we hear.
Okay.
Please.
Okay. First of all, I would like to thank you, Professor Karchenko, and Professor Nicolas Bardis to inviting me for this conference and to have the opportunity to present my work. And I also would like to offer my full support to the courageous Ukrainian people who are going through very difficult time since 2 years now. So I will share my screen. Sorry. Hop. Maybe this one. I think I don't have the right to share my screen. Ah, yes. Up. You are seeing my screen now? It's okay?
Yes, we see and we hear you. Welcome.
Okay, thank you very much. I will present you today my work on bio-inspired control of robots, specifically when robots are in interaction with human. So as you said in the introductions, I am a professor at École Nationale d'Ingénieurs de Brest in France, and I am teaching in the School of Engineer, and I am doing my research in the laboratory LabStick, who is a laboratory from the National Research Center in France. Just short information, the work I will present today was developed at the L'Oréal Lab in the University of Lorraine, Nancy, on the east part of France, and now I moved since October to the west part of France in this School of Engineers, so it's a new position for me. My talk will focus on the main questions: how we can make robots able to interact socially and physically to humans like humans. So it is a very, very important question for the future of robotics. And this question for me is based on two main points. So how we can inspire it from biology. We have to understand the coordination of movement in the human or in the mammalian. And also we have to understand what is learning abilities for these interactions. So the outline of my paper is as follows. First, I will introduce what is movement and human rhythmic movement for me, interpersonal coordination, synchrony and synchronization concept. And after I will introduce what are central pattern generators, which are specific neurons model. And also in the last part, I will show you some experiments with different kind of robots. And I will try to convince you that this approach is interesting to make some synchronization and coordination between humans and movement coordination between humans and robots. Okay, so what are human movement for me and for some colleagues? So we have two kinds of main movements. We have rhythmic movements and discrete movements. And rhythmic movements, for example, is locomotion when you are cleaning a table, brushing something, doing sport in basket, for example, when you are play with the balloon. So these are rhythmic movements, and these movements are main dynamics movement. On the opposite, we have discrete movement, who are when you are taking an object, when you are doing sport, in baskets also, when you have the ball and you give the ball to another person's. So these two movements, discrete and rhythmic movements, composed are movements specifically for the lower limb, the legs, and the upper limbs, lower limbs, sorry, and the upper limbs, the arms. One difference is that rhythmic movements are only dynamic, and discrete movement can be static or dynamic. Rhythmic movements are non-regular for upper limbs, for arms, but are regular for lower limbs, for when you are walking or running, for example, or when some animals are flying or swimming. And discrete movements are regular for upper limbs and non-regular for lower limbs. So rhythmic movements are very primitive and automatic in our life. And rhythmic movements are underlying interpersonal interactions and interpersonal coordinations. We will see that after. Interpersonal coordination are mainly involuntary. That is the main point of this work. For example, Interpersonal interaction are involuntary. When you are working with persons, we can observe that the foot of each person is touching the ground at the same time in phase or opposite phase. So it's a inconscious synchronization of work. It's the same in applause. It's more difficult to understand, but it has been proved when a lot of persons applaud in the same time, there are some mode of synchronization that appears between the persons, and some frequencies emerge from this number of persons. So the phenomenon of emergence of coordination is very powerful, and human cannot avoid involuntary dyadic motor coordination. I mean that it is very difficult when you are working with a person, you observe that you are synchronized to these persons, but if you want to desynchronize, you have to make some effort in your mind to say, okay, I have to desynchronize with my friends, etc., etc. It's called also the magnet effect when two persons are interacting with some hand games, like in this picture, for example. This interaction is based on two main aspects. So the individual part of each participant, so you want to do this gesture, and the share of coupling with the other persons. And this is the main aspect of this magnet effect. So between the two movements. So we can conclude that interpersonal coordination is based on synchronization of movement. Another experiment was done by Dumas and al. More than 10 years ago now. It's this very interesting experiment. So a person is looking at an avatar, or another person, for example, moving this object, and one person has this movement, oscillating movement, and the person is looking the other, not only the eyes, naturally. And we observe that spontaneously, the two persons are synchronized together in phase, like in this picture, or in opposite phase. So it's a spontaneous emergence of coordination or synchronization in phase or in antiphase. And we can observe this if we measure the different signals of arms, of objects, etc., etc. And as a physician knows, and electronician knows also, this is the most characteristic of nonlinear oscillators. So if you have two persons looking together, one person has his own dynamic of movement, the other person has another dynamic of movement, and so one person can be considered to an oscillator with his own rhythmic on frequency, and the other person also. And then you have two dynamic systems independent at the beginning, but they are looking together, and then they are coupling by the looking, and then you have only one dynamic system. And from any initial conditions, all the system, the global system composed by the two persons, is going and converge to a stable cycle, a limit cycle, And this is the main characteristic of nonlinear oscillators, called also relaxation oscillators. So interpersonal synchronization acts like a dynamical system based on two coupled nonlinear oscillators. And this approach can explain that a dynamic, a very stable dynamic, emerged from this interaction. So this is a manner to observe and to understand what happens, and then to propose new method to control robots when they interact with humans. And of course, a lot of persons from you knows what are nonlinear oscillators. So you have a condition, initial conditions, and the system is going in the phase plan to a limit cycle, and what are the other initial conditions is the same, for example, in this Van der Pol oscillator, which is very well known. So nonlinear oscillator exists everywhere in mechanics, in electronics, in fluids also, and they have stable limit cycles, but they have also some chaotic behavior sometimes. That's why it's difficult sometimes to control them or to implement them in robotics. One very interesting experiment is this one. I hope you are hearing the sound here. So we have a table with a lot of metronomes, and all metronomes are setting to with its own frequency, but they are the same. Metronomes are the same, so it's almost the same own frequency, natural frequency for each metronome. And we start randomly the metronome, and if you wait enough time, you will see, I will accelerate the video, you will see that the metronome, each metronome is oscillating at its own frequency, at its own phase, but time after time, you will observe a natural synchronization, the emergence of only one frequency of all the systems. So they are coupling together by the vibration of the table, and the table is also moving easily. So this accelerates the phenomena, but you can do that on a fixed table. It will be the same, but it will take more time. And then we can conclude that from any initial conditions, all the oscillators converge to only one frequency and one phase. And you have then the emergence of a global movement, global coordinations from several local oscillators. So this approach has been implemented to control robots, for example, the famous bio-robots of Åke Spiert from University of Lausanne. And you can consider at this time that each robot joint is like an oscillator. And then you can use the model of these oscillators to control one joint, and then one legs, and then a body with different joint, and then a complex body. And complex body is the body of animals, of dogs, of leg robots, and of humans, because we have legs, we have upper limbs, we have postures, and then it's a complex to control and complex to have emergence of coordination of movement, sorry. So we can observe this synchronization phenomena when two persons are handshaking together. For example, in this experience I did in École des Mines de Nancy. So two persons handshake together in different social conditions, happy, sad, or natural conditions, and we measure the force in the hands, the movements, etc., of the arms, and we can observe that for each experiment we have the same phenomena, convergence of hands, a phase of contact, and after mutual synchronization. So this is very important. This experiment is very important because we have interactions between two persons, which is a social interaction because we said, hello, how are you? Or I'm happy for you, or etc., etc. But it's also a physical interaction with a mechanical contact between the two hands and the control of the posture of the persons. So for us humans, it's very natural gesture, but for a robotics approach, it's very, very complex, because if you want to give a message by the body, by the person, so by the robotics, by the robot, you have to control the posture, control the gesture, the frequency, and the force, and the synchronization with the other persons. So it is very difficult gesture that we are doing each day, day after day. So we can say that in this context, in this experiment, handshaking acts like coupled nonlinear oscillators also. Nonlinear oscillators can be considered the body or the arms or in the joints. So why nonlinear oscillators? In 1966, an important experiment has been done by scientists and called DESSERT'. So the experiment consists of understand the locomotion mechanisms. And they put the cats on the treadmills and they cut the links between the brain and the spinal cords. And with electrical stimuli, they start the walk of the cat. But they observe when the treadmill accelerates, the rhythmic of locomotion change. So by these experiments, they prove that the locomotion is not controlled by the brain, but by specific neural circuits in the spinal cord. And the locomotion is totally independent from the brain, except start signals, but after the control and the modulation of the control is local and controlled by neural structure localized in the spinal cords. So this was very important because they show that locomotion and rhythmic movements follow some automatic procedures and automatic patterns. And since this time, a lot of work has been done, and we have now several results from the biology, and we know that some CPG called central pattern generators are located in the spinal cord, so specific neural networks are in charge to control the movement and the rhythmic movement. So these structures are described by this picture, for example. So we have several levels, rhythmic level, pattern formation level, and after the control level or the low level, motor level. And we have this rhythmic level composed by two kind of generators for extension of movement and for flexor side, for extensor side, for flexor side. And this rhythmic generator level sends rhythmic signals to the pattern formation level, who modulate the signals and set the signals to the muscle through motor neurons. And we had feedbacks at each level. So it is artist description, but it is the main description we have. And now we have more information, more details. For example, in this picture from the same authors, we have on the left, on the right, arm or legs. For example, it can be the hips. So we have the same structure on the right, on the left, but we have a rhythmic level, modulation, pattern formation level and modulation level with oscillator here and interneurons, inhibiting neurons, etc., to make the movement in flexor, extension, and flexor and inflection and extension, and to have the synchronization between the two limbs and also in each limbs. So for upper limbs and legs, we think that it is the same. So we can describe this by this scheme, we have signals coming from the brain, of course, like, okay, I want to walk, I want to run, etc., etc. I want to brush the table. We have CPG for the left arm, CPG for the right arm, CPGs, many CPGs located in different, in the spinal cord, but to control different joints, and interneural reflex network also, under several feedbacks. So this description is absolutely interesting, but also it's too large for us and we have no details. So we have to propose different kind of computational scheme. And then is the question of the model. What is the computational model of central pattern recognition we have to use? So many works has been done, and I will show only the 2 or 3 important works in this domain. The first one was from Taga in 1995. He used the model of Matsuoka. We will see this model of central pattern generators has been used in a lot of works. So he used the Matsuoka model to control and to simulate the work of a biped in biped system. So he proposed this architecture. So 2 neurons, and 1 neuron is described by these 2 differential equations there. And 2 neurons are coupled together, and 1 neuron for the trunk, 1 neuron for the hips, the knee, the ankle, etc. Some links between the 2 CPGs from each leg. So I will not give the details, but it's a complex architecture. But what is important is the description of the Matsuoka model. proposed by Matsuoka in 1985. So it's a couplet, nonlinear differential equation couplet together. And we have two constant time. One is to describe the electrical effect in the biological neuron, and the other one is to the chemical effect in the biological neurons. And we have a function that is describe some links between the two equations, the function f, which is the max function. And we have here the networks, the neural networks with different weights, and also different, we said current, but it's a different information for the neurons, internal information of the networks or coupling from the to the other neurons, and different signals coming from the system, from articular system, speed, force, and from the environment to, for example, the contact ground. So this neurons is a nonlinear oscillator with specific input, and this input, will change the natural frequency of these oscillators, and this natural frequency is set by the constant time and the different parameters. Yes, I just this model is called mesoscopic model because we are not in a microscopic model of the neurons, but an intermediate level. And we have macroscopic and mesoscopic other models also. The HOP model proposed by Ispirt also, which is a more simple model, but the same approach to differential equations, coupling, weights, etc. And an external signal F, which forces the oscillator to change its frequency. And we can control human robot for working in forward and backward with this architecture without any model of the robot. And the Matsuoka oscillators were also used by Kasuga for handshaking, and he proposed this scheme with two oscillators coupled together, and the output of this CPG, central potentiometers, is controlling the different joint of the robot. And we have also external signals has input to the oscillators, and these signals, external signals, are also forcing signals that will change the frequency, and change because of this phenomena of synchronization that we observe together with the metronomes. So if we want to have a computation model of central pattern generators, we have to propose a scheme, and we propose this scheme on the right here. So we have 3 levels, and rhythmic level, formation levels, motor levels, and we propose, I will show you after the model we use in this model, and we have the descending signals coming from upper level, from the brain, for example, or for the high level of the robot. So we have the rhythmic level with 2 oscillators sending signals to interneurons, and after we send information to the flexor or extensor. But when we are controlling a robot, we don't have muscles, so we have to change this motor level. And the main question is about the feedbacks. So sensory feedback, which kind of sensory feedbacks and for which level? This is a very difficult question. We use since many years now the model proposed by Rowat and Silverstone in 1993 because it's a generalization of the Van der Pol oscillator that I talked rapidly before. So the RS, Rowat-Silverstone model, is based on 2 differential equations with 2 constant time also, like I said before, one for electrical phenomena in the biological neuron and one from the chemical phenomena in the biological neurons. We have a function F for the coupling, and we have different kind of injected currents or inputs. This model is very interesting because the function F is a hyperbolic tangent function, based on one parameter, and depending on the parameter, the function F has different kind of shape. So she can be linear, nonlinear, and nonlinear with a negative slope, and then we have oscillation in this condition. And this model can reproduce the four main behavior of biological neurons observed by the biologist in the spinal cord, like it can be shown here. So we have four main behaviors: oscillating behavior, potential plateau behavior, post-inhibition rebound, and adaptation of discharge here. And what is important finally is that we have oscillating modes and non-oscillating modes. And we can control the frequency of this oscillation. So we can build joint controller based on this equation that will have different kind of behavior depending on the two parameters here, sigma S and sigma F. And depending on these two parameters, we can have this behavior with no oscillation, and we can have oscillation here in the red part, and we can control the frequency of this oscillation. So finally, we can control the joint only by controlling the point of this surface with two parameters. So it's an articular kinetic index energy we propose here. So we can rewrite this Rawat-Silverstone model in this formalism, which is the van der Pol formalism. And in this case, we will have the opportunity to implement plasticity, I mean learning Hebbian rules proposed by Richetti before. So I will not give the detail here, but you have the equation. What is the main idea? The main idea is that your oscillator has a natural frequency based on the constant time and different parameters, sigma S, sigma F, etc. But when you change sigma S, you will change the natural frequency. And then if you change sigma S depending of an external signals F, which is the forcing signal, you will change the natural frequency of this oscillator. And then if you have a learning rule to change the sigma S, your oscillator is able to learn the frequency of this forcing signal, of this external signal. And then we can propose a scheme of a central pattern generator showing here. So we have the input signal, which is a signal F, forcing signals. We have two sides, extension here, friction here, rhythmic generator, which has oscillator, two oscillator with this equation connected together to have a mutual coordination. We have pattern formation level, who are only sigmoidal function there. And we have sensory neurons that send signals coming from the robot, from the joint, for example, velocity, acceleration, torques, or force from the environment, contact to the environment. So this is the generic model of one CPG to control one joint. So we use this approach to make some experiment on learning motor coordination between human and robots. And the main experiment was the waving back example. So you are saying hello robot, and the robot must say hello, how are you to you. So for that, we use the paper robot, which is a humanoid robot, and we implement a CPG for the shoulder, another one for the elbow, and the robot is looking the person. So we have the signals of the movement of the person, specifically the hand, has a visual signal. And we use these visual signals to force the first CPG. And the second CPG is forced by the output of the first CPG. So we have here a little circuitry composed by two CPG and several neurons. So this is the experiment. So you can see the persons waving to the robot, and the robot is looking. So we have the movement of the hand on the video, and we use these signals to control or to force the central pattern generator. And you can see here when the person is waving and accelerate, that the robot is also accelerate. And in synchronized to the persons. We can see the signal here. So the beginning of the experiment, low frequency, and after we accelerate the movement, and then the frequency increase, and the robot is following. And you can see the Hebbian plasticity, so the learning mechanism here that change the parameter. So we change the sigma S, and then we change the frequency. Same experiment here. And different experiment was done, of course. And we show that for this 10 waving, for example, we can show the synchronization phenomena by the phase log value index, which when you have 1, you are in synchronization, and 0, you are desynchronized. And then you can see that for each waving, we have the same phenomena. At the beginning, the robot is learning, so he tries to find the synchronization. After we have synchronization, we change the frequency. We have little desynchronization after synchronization again. And you can see the limit cycle of different phase plan here for the different parameters, position of articular position, etc., and phenomena of learning here. We do the same for more complex sign, for example, circle sign, infinite sign. So we use for that another CPG to have the movement in the space. So we have vertical signals, vertical movement of the hand, horizontal movement of the hand coming from the visual signals, and we control the CPGs for that. And we have exactly the same emergence of synchronization between the robot and the persons. And this is very important because the robot finally is not doing exactly the same gesture as the person, but is doing a gesture that has the same meaning. The waving, I want to do cuckoo, I want to do a circle, I want to do infinite sign to a person. Okay, so it's not exactly the methodology to control industrial robot to do very precise task, but we will see that we can use this approach to control industrial robot for specific industrial tasks after. So we have the questions also to control human-robot interaction through specific games, but with the games we address the question of physical contact between human and robot through non-rigid object. And for that, we decided to experiment about the rope jumping, which is a famous game for children. So how we do that? We use industrial Franca robots here, and we implement CPG for elbow and shoulders, and we use the force at the end effector of the robot has forcing signals for the CPG, and the CPG is composed by 2 oscillators from Howard Silverstone here. So this is a CPG for 1 joint. So the force is input of this CPG, and we make the sum of the output to control the motors. So CPG for elbow, CPG for shoulders, the force measured here on the hand effectors, and the human is moving the rope here. And at the beginning, you can observe that the robot is not synchronized because the learning is going on. And after several seconds, the robot is doing exactly the same, is doing a circular movement with same frequency of the persons. And when we accelerate the movement, we have acceleration of the movement of the robot also. So this is experiment that was done last July, and we have submitted to ICRA, so I cannot give you more details for this. And we do also the handshaking with this robot because this robot can have parameters from torques, and we can control the torques, joint torques, and then we can associate joint torques, so impedance control of the robot, and active control from CPGs. One question is about rhythmic movement and discrete movement. Exactly, and briefly, the oscillating neuron of Howard Silverstone can behave as a PID controller. In different conditions, different values of the parameters, the oscillators became a PID controller. And this is very important because in this case, we can control discrete movement and rhythmic movement. So the phase of discrete movement was done at the beginning of the movement, and after you have the rhythmic movement when the robot is handshake to the persons. And we can see here the discrete movement on the joint phase of the free articulation of the robot. So the discrete movement, and after the rhythmic movement, and here on the cycle, limit cycle here, and for each joint. So we can combine rhythmic movement and discrete movement. And this is very important for industrial applications. And this is one example we have, we did for industrial application in a very very hard environment in siderurgic plant in the east of France. So a person must cleaning a very dangerous machine, and we can use this robot to make cleaning. So in the laboratory, we don't have this environment, but the goal was to propose a control scheme, and we propose this control scheme so the operator can be now far away from the system. He has an haptic or a joystick to control the robot, and he reproduces his movement on the joystick, and we have an oscillator that so nonlinear oscillator, robot zero-stone model, between the master and between the robot. So the oscillator send orders and send Cartesian position to the robot. We have the inverse kinematics control module of the robot, and the robot is moving, and we have feedbacks like the force on the between the hand effectors and the table. And we observe synchronization between the joystick, the robot, and then the oscillator. It means that the oscillator is merging dynamic movement or dynamics of the operator, dynamics of the robot, and is able to synchronize between the dynamic of the robot and the dynamic of the operator. And then the robot is synchronized to the dynamic of the operator. And we show that using this approach, we can decrease the power dissipation of the robot using the teleoperation in hybrid mode, using the CPG here in orange. We can decrease the power consumption of each motor of the robot. Okay, this is my conclusion. So bio-inspired control is an interesting approach in robotics because we can control rhythmic movement without using any dynamic model of the robot. We can use this natural properties of these oscillators to have the emergence of coordinations of movement between human and robot. And this is very important for intrapersonal and interpersonal coordination. We work also, I didn't present the work here, but we work also on the simulation of human walk with a neuromusculoskeletal model. And for future, we want to work on verbal gesture communication and also for different rhythmic tasks in dangerous environments or in industrial applications. So I would like to thank to my PhD students, past students and ongoing, and thank you for your attention.
Thank you very much, Professor Patrick. And now we have a very short time for question and answer. Welcome for your questions, dear colleagues. Would like?
Yeah, I wait for the questions. Thank you very much.
Thank you. Okay, Professor Shmilova, welcome.
Thank you. I have questions. I from National Aviation University, and very interesting report because we have system for diagnostic of emotional state of pilot in flight, but we have system for monitoring of movement of robot as human. And I have question about monitoring and control of movement of robot in job, and decision making if we have emergency in this situation. Did you have in your system a control of movement and decision making? And second question about discrete control or constant control, because this is a very important for control and decision making if we have emergency in little time in situation.
Yes, thank you for these questions. The controller we use are on the lower level of the control. And as you understand, we have some parameters who can be changed to change the functioning, the behavior of the oscillators, okay? So these parameters can be controlled by higher level, decision-making level, for example. So that's why we can consider that what I present is just a part of a bioinspired, more general bioinspired system who is able to detect emotion condition of the system, of the persons, and then change the parameters. So we do that, we did that, sorry, for reflex behavior on walking. So the robot is walking and he was hurt by a ball, and then we change suddenly the parameters, and then we have a reflex behavior. And about emotion, I am working also on this on these questions, how we can recognize emotion of a person. And then you know that emotion depends on the posture of the person, but also the frequency of the movement. And so we made some experiment with different students. We can synchronize the central pattern generators networks by observe the rhythmic movement of the persons by using some video, some movement capture system, sorry. We can synchronize the central pattern generators to the frequency of the person, and then we can detect what is this kind of frequency.
Yes,
if it is, yeah.
But who decision making in emergency, robot or human? If we automatic
system. This is a global question, so a very important question. Who has the decision finally, the robot or the human? I don't work on these questions. My opinion is that
maybe collaborative decision making.
Yes, exactly. Exactly. Yeah. We can use artificial intelligence to detect some specific condition very rapidly, more rapidly than a human, but we can propose different solutions to the human. Yes, it's a great, very important question.
Approach in your investigation.
Thank you.
Any other questions? No. Once more, thank you very much, Patrick, for your extremely interesting report, for your contribution. Thank you very much. And
thank you, Slava.
We wish you success and hope for new meetings in your country, in Ukraine, in Europe.
Yes, I hope.
Thank you.
No
you
problem.
very much.
Yes, thank you. Good luck for you, and I wish you a very good conference. Thank you for inviting me again. Thank you.
Okay. Now we would like to invite for the next keynote presentation. It's my pleasure to invite Professor Alexander Litichevsky. Alexander is Doctor of Physical Mathematical Science, and Alexander represents very famous Institute of Cybernetics named after Viktor Glushkov, National Academy of Science of Ukraine. Alexander is head of Department of Theory of Automata, and Alexander has huge experience in not only research in industrial application with famous companies of the world, such as Intel, Motorola, and so on. Alexander worked with his team in area algebraic methods of development and verification complex system, including systems, embedded system for critical application based on the FPGA technology and so on. It's my pleasure to invite Alexander for your keynote lecture. Welcome, Alexander.
Hello, everybody. Can you see my slides?
Yes, we see, we hear you. Welcome.
Okay, thank you very much. So I'm, as Vyacheslav said, that I'm a head of the department of the theory of digital automata, or the Institute of Cybernetic, Glushkov Institute of Cybernetic, and our team. And we are the followers of the well-known algebraic school of Viktor Glushkov, and it includes of dozens of outstanding scientists who have been active for 3 generations. So the algebraic school is known both for its theoretical and practical achievements. Back in the 60s, one of the first computers with the ability to perform deductive inference at the level of machine instruction was created. It was the Mir machines series, which unfortunately was not implemented on a mass scale. The department that I manage is the department that was managed by the outstanding Ukrainian algebraist Viktor Glushkov, the founder of our algebraic school. The achievements of the school include the algebra of algorithm, algebraic programming. The modern technology of insertion modeling is widely used in various subject areas such as verification and testing, verification of security and liveness properties of such subject areas as the creation software system, the hardware industry, blockchain, and in research in modern physics, chemistry, and biology, and other. And of course, one of the main direction of our institute, personally my research and my students, is the cybersecurity, where the algebraic school has introduced a new approaches and methodology over the last decade. My presentation refers the presentation of the neuro-symbolic approach in cybersecurity, which combines modern trends in the use of artificial intelligence methods and advance in the use of algebraic methods in cybersecurity, especially in detection of cyber attacks. Detecting a real-time attack on a network or computer system is a critical cybersecurity challenge that have been the focus of much engineering and scientific development. Today's cybersecurity industry uses intrusion detection systems that have evolved from previous security features such as network firewalls and VPN, virtual private networks. Intrusion detection system, IDS, provide 2 main functions. One, the detection of unwanted behavior in the form of anomalies, and 2, data collection with analysis of activity in network protocol and comparison with so-called signatures that contain features of possible attacks. However, IDS are triggered when an attack has already occurred. Therefore, there is the question of neutralizing attacks, for which intrusion detection and prevention system, IDPS, were created, which constantly scan network actively and block network traffic in the case of attack even before an intrusion. IDS require signature of known attacks and virtual place in the system database in various specification, for example, in the form of condition they present a logical expression in some formal language if the else expression. If the condition representing a particular intrusion is true for the protocol parameter, then an alarm is triggered. Intrusion detection is more difficult when intrusion have occurred over a period of time or contain intrusion signature in different packets or protocol traffic, packets of protocol traffic. There are various methods for overcoming this, especially using finite state machine for signature presentation. Alternative language of string patterns or semantic condition can be used. Also, time stretched intrusions are not always detected. The signature compression method used by EDS is an effective method that shows accurate result in detected known attacks. However, they're powerless to detect zero-day attacks, that is, unknown previous attacks, and when data is constantly changed by hackers. Minimal changes in the parameter of hackers' attacks can lead to a case where the signature compression doesn't work. An anomaly detection system, however, can detect intrusion defined as deviation from the normal behavior of network activity. This system fall into several types, but the main type is based on machine learning, which has proven efficiency at both classifying known attacks and detecting anomaly. Deep learning neural networks, which can classify network protocol behavior as abnormal, are able to quickly detect attacks. More advanced neural systems detect a type of attack according to its classification model. Neural networks are built by learning on certain data set collected in the process of observing the behavior of network protocol. The simplest and most visible method of real-time attack is to detect anomalous behavior that does not correspond to normal action of the protocol, but at the same time error may occur because violation of normal behavior may be caused not only by intrusion into system, but also by improper uses of resources, user errors, or errors of programs running in the environment. However, it is quite difficult and in many cases impossible to create a data set that covers all scenarios of normal behavior, even up to the same equivalence classes. Therefore, system can classify the attacks or the causes of anomalies and prefer, but such systems do not detect attack for which no training set has been created. A more reliable way to prevent attacks is via symbolic modeling methods. This was first confirmed at the 2016 competition for detecting vulnerabilities and detection cyber attacks by DARPA agency, where the first three medalists used a symbolic approach. The main methods of preventing attack is the detection of vulnerability in system using formal methods, especially symbolic modeling. In our institute, we implemented the symbolic or algebraic approach that was used first for detection of vulnerability and was deployed on the multiprocessing system supercomputer SCID-3. Now it is used for defense of critical structure objects. Algebraic approach turned out to be quite suitable for detecting attacks. The corresponding prototype of intrusion detection system was developed symbolic modeling, and let's consider it. First, I like to present in algebraic approach the following theories and methods that have been used. So first it's algebra of behavior with a very developed mathematical apparatus for the formalization of network environments such as traffic network protocols as behavioral equations, and many formal methods were developed using this model. The known behavior of attacker can be formally described using behavior equations as well. We use the theory of agents and environment for formalization of entities operating in the intrusion detection system environment. Behavior algebra is a two-sorted algebra, universal algebra over the set of behavior and over the set of the action of agents. This algebra has two operations, three terminals, constant and approximation relation. The operations are prefixing, alternative choice of behavior. The terminal constants are successful termination, deadlock, and divergent behavior. The approximation relation is a partial order on the set of behavior with minimal element. Behavior algebra is also enriched by two operations, parallel and sequential composition of behavior. Every agent's action semantic is defined as the triple where we have a precondition of action presented as the formula in some theory, a process that illustrates the agent's transition between states and the post-condition. We consider behavior pattern of behavior equations with the arbitrary behaviors. If initial state of agent and environment be represented by some initial formula, we can, starting from the initial formula, apply the action and unfolding the behavior algebra equation. This process is called algebraic modeling. Algebraic matching is the method of finding behavior corresponding to the pattern in the behavior equation system. It shall be implemented by resolving of behavior equation. Over here we see the algebraic signature stack damage attack. It's represented by behavior equations on this slide. We can see the pattern of attack with arbitrary part of behavior and possible actions of intruder. The semantic of processor instructions, syscall, move, is presented in the equations and defined by corresponding actions. The pattern is created manually. So we should involve some expert in cybersecurity to review these patterns to avoid the errors in the pattern. To detect an attack in the binary code, for example, of the software system, it is necessary to have a model of the system, of this code, of the hardware, of the object which is under attack. We should have a model of this system in the algebra of behavior. If the attack patterns or algebraic signature are created manually, the system model is created by a corresponding translator that generate the system of behavior equations and set of action automatically. You can see on this slide the set of Intel x86 instruction converted to algebraic specification automatically. So how does it work? The intrusion detection and prevention system receives incoming data from the external environment and quarantine it. However, based on the input data, a behavioral model of the system, which can be targeted by attack, is launched, and with the help of modeling, the corresponding behavior is generated. Next, an algebraic matching is made of the possible attack pattern with the generated behavior. If the event that match has occurred and the generated behavior has reached the end of the attack, the data is blocked completely and an attack warning is issued. If the attack has not reached the end, Then the next portion of data is accepted and the procedure is repeated again. If the magic did not take place, then the data is passed, the next portion of data is passed to the system. So we see the following benefits. Detection of vulnerability of attacks is accurate, corresponding to the pattern. There are no false positive. But we also have the disadvantages of this method. It's first time-consuming, complicated computation because we use different solvers, proving machine. And the second disadvantage is the long period of manual creation of pattern, but algebraic and cybersecurity experts. It was the algebraic, but we also have another approach that we also implement in the institute. So we work with the creation DNN for detection of botnet activity in a network. The botnet is a malicious software deployed after intrusion and causes DDoS, denial of service attacks. Another deep learning neural network was created for the detection of HTTP protocol attacks. Usually, an intrusion detection system that uses a neural network traffic is blocked when the intrusion is detected, but some systems also work like a firewall and prevent intrusion. In our case, we use also the traffic blocking when classifies the attack. To conduct an experiment to detect network intrusion based on neural network technologies, we need to first find the data sets that contain attack like ARP spoofing, wiretap, simple service discovery protocol, another kind of HTTP attacks. So after analyzing of series of data set, the most suitable data set was Kitsune. The data set was assembled in 2019 and updated in 2020, make it one of the most advanced data set to date. The dataset covers many different attacks and contains millions of records generated using a unique algorithm of feature extraction. So we also, for feature extraction, use after image extraction tools. The tools is unique. We use the sigmoid function as the activation function. So the dataset includes more 2 million rows and 80% of data we use for training and 20% we use for testing. So what are the problems? It's relatively low accuracy, much less than in the algebraic methods. A lot of false positive that cause unsuitable work of computer network. It is not resistant to adversarial attack. A small action of hackers, packet shuffling of time stretching of packets can cause misclassifications. A trained neural network should show high classification accuracy only in the scope of in the condition in which it was trained. So also we have some disbalance in different classification, more data for some types of attacks and less for another. So how we overcome all these problems in the scope of AI? First is the generation of augmented set at the level of the problem space. We define a set of transformation corresponding to real-world hacker actions. This is time-lapse operation, data permutation with the preservation of traffic semantics and plausibility. Also, we identify the most sensitive feature that affect the classification results and create data at the feature vector level. The system for analyzing neural network for the property of robustness. Also, we use the vehicle system was developed in Harvard University in the United Kingdom, Edinburgh, and was used in the verification Within this framework, a suitable language is developed which verify the property of robustness. It's determined by error between the expected and the obtained classification results. But the most efficient way to overcome these disadvantages of neural network was the usage of hybrid methods that combine AI detection and algebraic approach, or use a neuro-symbolic approach. The scheme is the following. As in the previous case, the input data is quarantined for some time. However, in this scheme, the neural network perceives the data earlier and determines the type of attack. The specified type of information is passed to the algebraic part in the database of patterns, and the corresponding algebraic matching task is activated, which provides confirmation that this attack was not a false positive. The procedure can be made more reliable when both components that confirm the attack work in parallel. In this case, all information will be checked by algebraic component, and the corresponding traffic analyzing time will be significantly increased, of course. However, if there is certainly that the neuron, there is that certainty that the neural network will not miss the attacks, then it is possible to use the fast action. So we have two modes, the fast modes in when the neural network is working all the time, and the classification model and analyze the data from the current time at a very high speed. The algebraic component is activated when the neural system detects a suspicious behavior only. And the other is enhanced mode, in which the data is perceived by the both components, accurately detects attacks, which was confirmed by the algebraic component of the neural network classification. This is the mode of self-learning of the neural network and the guidance of the algebraic system. This technology scheme was implemented and tested on for HTTP attack. With the parallel operation of the neural network and algebraic matching in the model of calling of algebraic confirmation of the classification attack, the time was reducing by 20 times. The accuracy of the classification increased to 90% when both components work sequentially. First neural network and confirmation, but algebraic, and when they worked in parallel, it was increased up to 100%. Also, in the second case, the detection time increased accordingly. So, what are the benefits? It's absence of false positive, good resistance to adversarial attacks. It's a training of DNA in a real condition in the enhanced model, high accuracy of detection, faster than algebraic approach. The algebraic method started only when neuron detects the suspicious behavior. But we have the significant disadvantage is it's still long manual creation of algebraic signature, algebraic patterns of attacks. So we have the composition of two classification models. One is neural network trained on example, and the second is the algebraic component and contain a model of the system to be protected as well as a pattern database. We call such composition a cognitive network, which comes from the Latin word cognitio, which translates cognition, study, awareness. Also, the term was used in several contexts, but now it's the context of cognitive network is quite difficult for It refers to the ability to mentally perceive and process external information. So we combine two components, this statistical experience and the ability to derive facts from knowledge. In general, their parallel work can be defined as learning based on example and conclusions from knowledge and making decisions based on experience and knowledge. In a general, a cognitive network is a multi-component entity that can include components that operate with knowledge in different ways. Machine learning, deductive and inductive inference, ontology, etc. We define the type of such network based on perception and the model in terms of algebra of behavior. So there are a lot of other examples of cognitive work. We can use it in the automation of proving of the theorem when the neural network is used to suggest the application of some relay or some formula, and the algebraic part it generate the next steps. So another possible application is the modeling we used in the modeling of scientific experiments in chemistry and biology, when the search of property of substance take place in the process of modeling, and having data scenario of the behavior. It is possible to speed up by limited it to the hints of neural network training on existing scenario. So this is the short survey, what we did, our achievements, to how to apply neurosymbolic approach in cybersecurity. So thank you for your time.
Thank you very much for your presentation, Alexander. Now we have time for questions, short discussion. Any question, please? I have short questions. Could you ask about answer about any metrics for assessment of trustworthiness of detection of different kind of attacks by use of your methods? I mean, how we can assess quantitative metrics to understand efficiency of such approach.
Okay, so we have metrics. The metrics is the time of detections, the time of detection. We have metrics for algebraic. It's much slower than AI, and it is slower than in the neurosymbolic approach. The other metric is the accuracy. The best accuracy was reached when neurosymbolic approach. It was so if using AI, we had accuracy 80% in the case of the algebraic model. We have accuracy 100%, but it was too slow. But in the case of neurosymbolic, we have accuracy more than 90s, and the good speed of detection of attacks. So these are two main metrics which we provided.
Thank you. And what is your opinion? Is it need, or is it possible to add your approach by more traditional approach based on traditional testing, similar penetration testing, or any other techniques? I mean, your approach is more theoretical based on neural and symbolic methods. And what about application these methods together with more experiment-oriented techniques, such as penetration testing, for example.
Okay, I think that penetration testing, if you have the data set for testing, of course, we can use them to try it we can try for testing of the technology, testing of the technology. So we have the model of project which we should to defend, to defeat, and we have the some AI, and so we can use penetration just for testing of technology. As for application in real life, we can it can be a good an additional some additional techniques for the current traditional methods that are used in intrusion detection systems.
Thank you. Thank you, Alexander. Any other questions? No. Thank you very much for your keynote lecture. We wish you new interesting result and hope for continuation of our cooperation with the DESSERT conference and our university, our teams. Thank you.
Thank you, Vislav. Thank you. Thank you.
Dear colleagues, we have finished our first plenary session. Thank you once more our speakers for extremely interesting presentation. We see that there is a connection between problem of robotic system and problem of cybersecurity, and I hope we will go ahead to communicate to provide synergy of this very interesting object and very interesting techniques to assess and assure cybersecurity and safety. Thank you very much for your contribution, for your attention. And now we finish our first plenary session. 15 minutes later, we will start our 3 workshops according with our schedule. I would like to workshop chairs to moderate your sessions. The first workshop it's related to modeling methods, Professor Simonov and Professor Kuchuk. Welcome. Second workshop related to intelligent cyber physical system, Professor Lysenko, Professor Sachenko, and Professor Markovsky. Welcome. And the third workshop on the human-machine interface for different applications for critical infrastructure as well, Professor Vladimir Zaslavsky and Professor Tatiana Shmileva. Welcome. Let's go ahead and see you later. Thank you very much.
Thank you very much. Bye.
Thank you. Bye. Have you any questions? Please ask us. I see a question from Vladimir Kolatusha. No. Okay.
And Vyacheslav, I have a question also.
Vladimir, nice to see
I would
you.
like to ask you about we closed this connection and open new line.
Yes,
Yeah?
yes. You
Okay.
need finish this connection and
Yes,
start according
start
with
yes,
link
yes.
at the program.
And you sent for us link with conference.
You can use link on the DESSERT website. You can use links from DESSERT website. Yes.
Okay, because yes,
because
super.
maybe some problem with
Connection. Yeah.
Okay.
And also I have some question for you. I have also connection in 4 p.m. With colleague from Swedish Institute for 1 hour. It's possible to change. Maybe Tatiana help me with.
Yes. You will moderate this workshop together with Professor Tatiana Shmilova. I think you can agree now to
help with.
To help with.
Yes, okay. I will inform she about it. Good. But now we will see you. I understand. Yes. Good. It's interesting.
Yes. Я теж дуже радий вас бачити, шановний Володимир Анатолійович.
Так. Хорошо. І після ввечері щось будемо думати. Добре.
Добре.